So here we'll talk about charge on isolated conductor. So here it says if an excess charge is placed on an isolated conductor, that amount of charge will move entirely to the surface of the conductor. None of the excess charge will be found within the body of the conductor. So this is a characteristic of the conductor. So for isolated conductor, what? Let me see. Okay. Okay. So it says for the isolated conductor, the charge will move entirely to the surface. Actually, it's something like that. Something like that. There will be no charge going to the inside part of the conductor, or of the conductor. So none of the charge will be found within the body of the conductor. Okay, so here it says here we have a large conductor. So the green one is the conductor. The green one is the conductor. The orange cylinder is just a Gaussian surface, which is only exists in the imaginary. It is not really a cylinder practically exists. It's not that case. The Gaussian surface is just from the imagination. We consider this surface is the Gaussian surface, and then we try to calculate the net flux. And then it doesn't really it does not necessarily need to be an exist object. Okay, so here we have a conductor which is very large, so extend to far away. It should extend to far away, but it just only shows this part, which is the cross section. And so it says the side view of a tiny portion of a large isolated. So it says it is large, but it only shows a tiny portion of it. So isolated conductor with excess positive charge on its surface, a cylindrical Gaussian surface embedded perpendicularly in the conductor. So you can see this is perpendicular to it, and half of it is inside the conductor, half of it is outside. So it encloses some of the charges. Electric field lines pierce the external end cap of the cylinder, but not the entire end cap. The external end cap has area A and area vector A. So here, if we try to apply the Gauss law here, we will know that for this one it says there is no E field inside the charge, and so as E field because there is no charge inside the conductor body. So if you try to define any Gaussian surface inside the E field, there should be zero then, and it means that there shouldn't be any E field inside a conductor. But for isolator, there could be excess charge inside the isolator, and so as E field. But for conductor, there should be very clean, no charge, no E field inside the conductor. Okay, so if you can accept this, then we'll move on, and we will see there is only E field pointing to the right side because it is all the way symmetric, because we assume that this conductor is infinitely large, which means this surface is infinitely large. So due to symmetric, the E field can only point to the right side, So far, we don't know whether it is uniform or not yet, but we only know all the E field should pointing to the right side for the outside part. For the inside part, there is no E field. So when we try to consider the flux for this cylinder, for the right surface, it will be E times A. It will be E times A. We doesn't necessarily know the E field for just say this point and this point will be the same. But for this surface, it has an equal distance to this plane. So we can know that the E field over this plane will be uniform. So we have nothing but E times A for this side. And for the other side, this part, there is no E, so there will be no flux for this plane. And for the side part, because the E field are parallel to this surface, which means perpendicular to the aerial vector. So there will be no contribution for this part, for the side part. So we only have EA, which is the total flux. This is the total flux. So when we apply the Gauss law for this Gaussian surface, we have epsilon naught times the total flux EA, and then it is the enclosed charge for this part. The enclosed charge is here. This is Q enclosed for this part. Okay, so we also use the term sigma, which is the surface charge density, as we use in the previous chapter, and then multiply by this area. So if we look at the left and right hand side of this equation, so we can just cancel A on both sides. So it turns out to be E equals sigma over epsilon naught, which is nothing but a constant, because sigma is a constant. We assume the charge density on the surface is uniform, and also epsilon naught is of course a constant. So this is a constant E field. So without the prior knowledge that the E field should be uniform over this x-axis, we finally find out that the E field will be uniform. Okay, so now we can recall this page from the previous chapter, which is equation 2226. We divided it in the previous chapter. We just try to separate this charge disk into many charge ring with different radius, and then we integrate from 0 to capital R to form a whole disk. Okay, and then at that part, if we assume that R is infinity, which means that this disk is infinitely large, then it will be a constant. So we have a sigma over 2 epsilon naught. Here we have a sigma over epsilon naught. So we have a factor of 2 here. Because here we assume that this conductor is infinitely large in terms of the surface, but also the thickness. So we don't have the E field contribute to the right side. But here, this is a very thin charge disk. So it will generate E field pointing to the top for the upper part, and E field pointing to the downward for the bottom part. So it's just like it separated E field into 2 directions. But for this part, we assume that E equals 0 for this whole area. It only contribute E field to the generate E field on the right hand side. So we have a factor of 2 here. If we just add them together, then that will be this one. Okay, so here we see another sample problem. So here it says a figure show a cross section of a sphere metal shell on inner radius r. So we have this sphere with some thickness. The inner radius is capital R. So a point charge of minus 5 microcoulomb is located at the distance r over 2 from the center of the shell. If the shell is electrically neutral, so this shell is neutral. So what are the induced charge on its inner and outer surface? Are those charges uniformly distributed? What is the field pattern inside and outside the shell? So it's like we have a charge here. So, and it is conductor. So the charge inside it are free to move. And of course, the total charge on this sphere will be zero. But we also know that the E field inside the conductor should be zero. So here we try to define a Gaussian surface which is inside this sphere, and of course the E field are all zero, which means that the total flux should be zero for this Gaussian surface. And if phi is zero, which means that the Q enclosed by this Gaussian surface will also be zero, which means that this charge is negative 5 mu c. So it will induce a positive 5 mu c charge for the inner surface. So we have plus 5 mu c charge on the inner surface. However, the total charge for this sphere should be zero, which means that it will also induce a negative charge on the outer surface. So we will have negative 5 mu c here, plus 5 mu c for the inner surface. Yeah. So it says, the negative charge will be uniform distributed, but for the positive charge, it is not uniform distributed because for this part, the force attracting the positive charge and negative charge will be stronger. So this side will be dense, and for this part, the charge density is smaller for the inner surface. But for the negative charge, it is uniform distributed. It is a bit strange, but not so important. Maybe you need to use some computer simulation software to redefine whether it is distributed like this, or maybe uniform distributed is a bit strange. But it makes some sense because if you also try to define some Gaussian surface outside, and you will find the E field should be uniform. I'm doubted about this one. maybe somehow uniform, but not necessarily exactly uniform. I'm not really sure about that. But not so important at this point. Okay, so next we talk about another one. So we are applying Gauss law for different symmetrical structure. We try to derive some of the expression for E field generated by some specific structure. So this case is like we have a infinitely long cylindrical plastic rod. So we have a plastic rod here with a uniform charge density lambda, and also it is infinitely long, although it is not shown here. So it is infinitely long. Okay, so here we try to define a Gaussian surface, which is a cylindrical shape. And of course, the axis of this cylinder is parallel to this rod. And of course, the center is actually on this rod. So here we try to apply Gauss law for this Gaussian surface. Okay, so here to find the field at radius r, So this is r, the radius r. So we enclose a section of the rod with a concentric Gaussian cylinder of radius r and height h. The h is not very important because it turns out to be cancelled. So, but here we just assume this variable here. The net flux through the cylinder from the Gauss law reduced to this one. So we can imagine for the fixed distance r, small r, the E field should be uniform. Although with different r, the E might be different. But yeah, for this cylinder, the E should be constant. So it is somehow like E dot dA. So E should be in radial distance, which means E dot dA is nothing but EDA. And then E is a constant, so it is nothing but E times A. So for the cylinder, if you just try to cut it like this, and then you expand it, so it becomes a rectangle. So this is the height, and then this is the width. The width will be 2 pi r. So it turns out to be like this. If you try to cut it out, you know this surface area of the side of this cylinder. So the total area for that part will be 2 pi rh. So we have 2 pi rh here. So EA is E times 2 pi rh, which is this one. And then for the Gauss law, we have epsilon naught times the net flux equals the Q enclosed. And of course, for this one and that one, the E field is perpendicular to the surface, so it doesn't contribute anything to the total flux. Okay, so for the Q enclosed, as we know, okay, so yeah, so here for the charge density, we know that the charge density is uniform, which is lambda here. So the total charge enclosed by this cylinder will be h times this charge density lambda. So we have lambda h here, and of course we go to here, and then we can just move these terms to the right side. So we finally find that yeah, h and h can be cancelled. So we have lambda over 2 pi epsilon naught r like this. Okay. Okay. Any questions? Okay. So next, we would like to consider this one, the difference between this one and this one is that here we have a thin infinite non-conducting sheet. Conducting or non-conducting is not very important. Yeah, even for non-conducting, even for conducting sheet is still okay. But the point here is that it is thin. Okay, so with a uniform positive surface charge density, sigma. So here, So here we have the thin conducting plate with uniform charge density. So here we also define the Gaussian surface like this, which is a cylinder and perpendicular to this plane, and half of it is on the left side, half of it is on the right side. So it will, for the cross section, it will be somehow like that. This is the plate. This is the Gaussian surface, and in the cross section it is just a rectangle. Okay, so here, yeah, we have, let's say, so we apply the Gauss law for this Gaussian surface. So this is the Gauss law, and we see that for this plane, the area vector point to the right side, for this plane, area vector point to the left side, and so as the E field. So we have E times A plus E times A for the total flux. And of course, we can, at first try to make it symmetric so that, due to symmetric, E is uniform for this plane and also this plane. Like this. So we have 2EA for the total flux. And for the charge, enclosed by this Gaussian surface, it is sigma, which is the surface charge density, times the area of this circle, which is this one. Okay, so sigma A is the charge enclosed. So finally, AAA could be cancelled. AAA could be cancelled. So here we have a 2 epsilon naught E equals sigma. So E equals sigma over 2 epsilon naught. So which matches this one. But here we only use the Gauss law here, and then we just derive it like step 1, step 2, and done. But here, if you still remember, we try to define it to be a disk, and then we try to separate into many rings. And before that, we also try to calculate the E field generated by this ring, and then we integrate it over 0 to capital R. And then we find this expression, and then we let R tends to infinity to simplify the expression like this, which means that, of course, you can just use the Coulomb's law and also something like the integration to find the E field by generated by some specific structure. It will be quite tedious to derive that. You probably need some calculus knowledge to finish all those stuff. Here, the calculation will be simple, but the prior knowledge might be more difficult. Even actually, you need to know what is Gauss law, what is surface integral. But if you can really apply the Gauss law, then the calculation will probably be much easier than using this way. And of course, they should provide the same answer if it is calculatable. Okay, so here, here we talk about two conducting plate. So here we assume there is two conducting plate. So let us consider this one, part A and part B first. So here we have conducting plate. The surface integral on the surface charge density. The surface charge density on both sides will be sigma 1, and this is a positive charge. So due to this one, I just mentioned that it doesn't really matter is conducting or not conducting. So here, if we have a two conducting plate, but here conducting is doesn't matter for this part. So we use two conducting plate here. Here, yeah, so we have sigma 1 on both sides, and then we can find that E plus will be sigma 1 over 2 epsilon naught for this side and for that side. And for this one, it has exactly the same charge density, sigma 1, but it is a negative charge. So in this case, the E field pointing towards the plate rather than pointing outward from the plate. But the magnitude of the E field should be the same. So now we place these two conducting plate, charge conducting plate together. In that case, the opposite sign of charge will attract each other, which means all the positive charge will go to the right-hand side of this conductor, and the negative side will go to the left plane. And of course, the charge density will double because, yeah, sigma 1 on left side, sigma 1 on right side for this one, and then here all the charge go to the right side, so the charge density will double from these two cases. Okay, so we have E plus equals this one, 2 times epsilon 1 over 2 times epsilon 2. So as this one, which means that inside the two conducting plate, yeah, the total E field will be E plus E minus, because for E plus it points to the right side. For E minus also point to the right side because it's pointing towards the plate. It's pointing outward from the plate. So E1, E plus and E minus points to the same direction, so that they add up together. So finally, it becomes 2 epsilon 1 over 2 epsilon naught, 2 sigma 1 over 2 epsilon naught plus 2 sigma 1 over 2 epsilon naught, which becomes 2 sigma 1 over epsilon naught. And here we define the new surface charge density because making it 2 times sigma 1 is strange. So we just replace sigma 2 sigma 1 by sigma and put it here. Also, you can imagine that this is sigma 1 over 2 sigma naught. So if we just remove this part, for the inner part, we have E plus E. So we have 2 times of this term. It becomes this one and this one. And for this part, it is like E, this E and this E points to the opposite direction because it will extend to this side, which means that the E field generated by the negative plate points to this side and points to this side. And the E field points to generated by the positive plate will be pointing this side and pointing this side, like this. Something like this. So for this part, this one and this one will cancel each other, so that there is approximately low electric field generated on the left side. And so as this case, this is pointing to the right side, it's pointing to the left side with the same magnitude. So no E field outside the parallel plate. But for the inner part, they point to the same direction so that they add up. So this is known as the capacitor, and most of you are ECE students, so you should have learned the circuit analysis. You know what is a capacitor. And yeah. maybe for some of you should know it in high school physics, maybe. Okay, so let's see a sample problem. Okay, here, a portion of two large parallel conducting sheet, each with a fixed uniform charge on one side. The magnitude of charge density sigma plus for the positive charge plate and sigma negative for the negative charge plate. Find the electric field A to the left of the plate. So which means we would like to find EL, EB, and E right. E right. B is between. Okay. So it is easy. E plus will be sigma plus over 2 epsilon naught. And it is 6.8 times 10 to minus 6 over 2 times 8.85 times 10 to minus 12. So E plus generate like this, E plus. So this number will be 3.84 times 10 to the fifth power Newton per Coulomb. And then for E minus, it is sigma negative over 2 epsilon naught. So for this plate, it generates E field pointing to this plate, E field pointing to this plate. So it is 4.3 times 10 to minus 6 over 2 times 10 to 2 times 8.85 times 10 to minus 12. Okay, so it will be 2.43 times 10 to the fifth power Newton per Coulomb. Okay, so we have EL, which will be EL, which is this part. So we have E plus minus E minus, E plus minus E minus, which is 1.41 times 10 to the fifth power Newton per Coulomb, pointing to the left side. Okay, for E between this part, E plus point to right side, E minus point to right side. So we have E plus E minus. So it will be 6.27 times 10 to the fifth power Newton per Coulomb onto the right side. Yeah. And then for part, for ER, for part C, ER is this one. So we have E plus point to right side, E minus point to left side. So we have E plus minus E minus, which is 1.41 times 10 to the fifth power Newton per Coulomb, pointing to the right side. Okay. Yeah. Okay, I don't actually need this, please. Okay, so any questions up till now? So, okay, here. Here we talk about applying Gauss law for spherical symmetry. So in chapter 21, we mentioned that there is true shell theorem. At that time, I was not able to tell you why it is correct, but here we can use the Gauss law to really explain why it will be like that. So here it says for the first shell theorem, it says a shell of uniform charge attract or repel a charged particle that is outside the shell, as if the shell charge will concentrate at the center of the shell. So here we assume this is the shell. This is the shell with the charge Q, with the charge Q. Okay, so now we assume the Gaussian surface S2, which has a larger radius than this sphere. Yeah, the sphere for this the radius for this sphere is capital R, and the distance or the radius of S2 is small r, which is larger than capital R. So for this case, and of course we can just simply apply the Gauss law for S2, and then we can finally find this one. I've already derived it in the previous slide, so I don't repeat the procedure. But you can simply find that we have symmetrical distribution of the charge, and of course the E field is uniform. So the E field on the surface on the Gaussian surface should also be uniform. So we get this expression. And for the other shell theorem, it says if a charged particle is located inside a shell of uniform charge, there is no electrostatic force on the particle from the shell. Okay, so here for this case, we assume the Gaussian surface S1, which has a smaller radius than the sphere. So here, we can clearly see that there is no charge enclosed by this S1, which means that Q, we have Q enclosed to be 0. So we have phi to be 0, and of course the phi is 0, and the E field should also be uniform distributed. So all the points should be 0, rather than some of the point the E is positive, some of the point the E is negative, and then they turns out cancel perfectly. Not that case, because the E is uniform. So we can only have a E is 0 inside the sphere. And the point here, we assume the charge is uniform distributed, uniform charge. This is an important condition here. Okay. So next, it talks about other cases. So it is not a conducting sphere anymore. It is a non-conducting sphere with uniform charge density. So here we assume this is the sphere. This is the sphere with uniform charge density. Uniform charge density. Uniform charge density. So here, the uniform charge density, we denote it as rho. Rho equals to the total charge Q, and then the volume of the sphere will be 4/3 pi r cube. So this is the volume of a sphere. So I suppose you should have learned it in high school. So this one. And likewise, we also define the Gaussian surface inside this sphere, with small r to be the radius of this Gaussian surface. So here, as much as the charge density is uniform, so we have Q enclosed by this Gaussian surface to be Q, E, and C, and then the volume of this Gaussian surface in volume enclosed by this Gaussian surface to be 4/3 pi small r cube. Yeah. So here we can just cancel 4/3 pi. we will have Q enclosed. We move this term to this side and then just swap them. So we will have R cube over capital R cube times Q, like this. So this is the Q enclosed when we try to apply Gauss law to this Gaussian surface. Okay, so applying Gauss law. So this is epsilon naught times the total flux. Total flux is uniform because the charge density is uniform. And then, so we have E times the surface area, which is 4 pi R squared here. And then Q enclosed is this term. Q enclosed is this term. So we have expression like this. And if we look at the extreme left and extreme right of this equation, we can see we have 4 pi epsilon naught here. And then R squared and R cube can be partly cancelled. So we have R here. We have R here. R squared and R cube. We have R here. And then we have capital R cube, and then Q here, like this. So inside a uniform distributed charge sphere, the E field is linearly increased. It is proportional. It is proportional to R. All the other terms are constant. This is constant. Capital R cube is constant. Q is constant. So it's proportional to R. And if we consider the E field outside this sphere, we have nothing special because all the charge is enclosed by this Gaussian surface. So it is nothing but E equals 1 over 4 pi epsilon naught Q over R squared. So we don't repeat because, although the charge distribution are a bit different, but the Q enclosed is actually the same, and on the left hand side is still the same. So E should be something like this if we apply the Gauss law for this one. So this one is inverse proportional to R squared. Inverse proportional to R squared. Okay, so if we try to plot this out, it is like this is the R axis, the distance from the center of the sphere and to the point we concern, and then this is the E field. So when R is smaller than capital R, it is linearly increased. And after R is larger than capital R, then it is inverse proportional to R squared, which is decreasing. Okay, so this point will be Q over 4 pi epsilon naught R squared, which means that you just need to substitute R equals to capital R squared. Then this one will be this, or this one will be this. So this is continuous. Okay. Well, let me. Okay, let me try to finish this additional example. So this is the problem, the problem in the textbook, the problem 11. So it says the volume charge density of a solid conducting sphere of a radius R to be 5.6 centimeter radius with radial distance R, given by this one. So what is the total charge? What is the total charge? So for the total charge, we actually need to use the triple integral of the rho S, something like that. So it looks so horrible, but actually not really. Yeah. So actually, suppose we have a sphere. The charge density is related to the R. This is R axis. So which means that it is increasing. If R is larger, the charge density is larger, which means that there is no charge at the center, right at the center, and start to increase. And on the surface, the charge density is maximized. Okay, so in order to deal with this triple integral, we need to use the spherical coordinate, which is like 0 to 2 pi, and then 0 to pi, and then 0 to r. Rho, let us call this term to be rho s. So we have rho s times r over capital R. And then for this dv, it should be like r squared sine theta dr d theta d phi. So rather than using dx dy dz here we will usually use the spherical coordinate. So this one is defined by r theta phi. R is the distance from this point to the origin, and theta and phi will be you just project it to the xy plane, and the angle here will be theta, and the phi will be this angle. But assume you need to calculate the volume of a cube here, so it should be like this one. Okay, it looks horrible, but actually not. So we have phi SR to be constant. We have R cube. So we have R cube dr like this. And then sine theta. We have integrated from 0 to, oh, this one is theta, this one is phi. Let me draw it in a better way. So this angle, if we try to project it to the xy plane this way, so this angle will be phi. This angle will be phi, and the angle from z-axis to this one will be theta. Actually, if you would like to know more about that, you can just check it on Wikipedia. There's plenty of information about that. Okay, and d phi we just integrate from 0 to 2 pi. So this is easy to calculate because this is r to the 4th power over 4. This is theta. So this one is nothing but 2, because it is cosine of theta, negative cosine of theta evaluated from 0 to pi. So cosine of 0 is 1, cosine pi is negative 1. And then if you just subtract them, then it will be 2. So this is 2 pi. So finally, we have pi rho s r cube. And when we try to plug in the value, we have 3.14 times 3.54 times 10 to minus 12 times 0.056 cube, which is the radius of this sphere. So it is 1.95 femtocoulomb, like this. Okay, so next we will try to consider the E field at R equals 0. So it will be easy because it is nothing but 0. It's nothing but 0. Because you just consider the point here. And then for part C, Q enclosed inside this sphere will be like, similarly, we have rho S over capital R from 0 to R and R cube dr prime, which is actually the same as the previous one, except the upper limit is different. E5. So finally, we only have this term to be different, because if we have a sphere, we consider R to be R over 3. So we just integrate over this part only. So here we have yeah. Oh, this is rho S over R. This is R to the 4th power over 4. This is 2. This is 2 pi. So we have 4, 2, 2 to be cancelled. And then it turns out to be pi rho S R to the 4th power over R over capital R. And then we can apply the Gauss law, which is like epsilon naught times E times 4 pi R squared equals pi rho S R to the 4th power over capital R. So part of the R will be cancelled. It turns out to be E equals 1 over 4 pi epsilon naught. Of course, we need to times pi. Let's see. We have 4 pi epsilon naught here. Rho S R to the 2nd power over R. Yeah. Yeah. So capital R. Okay. So if we just plug in the values, we have 8.89 times 10 to the 9th power times pi times 35.4 times 10 to minus 12 times R square is 0.056 over 3 square over 0.056. So this number should be 6.22 times 10 to the minus 3rd power Newton per Coulomb. Okay. Okay, so let me finish off this quickly. Okay, so now we have a Q equals pi rho S R cube, because we consider the whole sphere. So this is from part A. Equals epsilon naught E times 4 pi R squared, which is nothing special. So we should have E equals rho S over 4 epsilon naught times R cube over R squared, like this. So if we just put in R equal to capital R, we will have rho S over 4 epsilon naught times R. So it is nothing but 35.4 times 10 to the 12th power over 4 times 8.85 times 10 to the minus 12th power equals 5.6 times 0.056. 5.60 times 10 to minus 2 Newton per Coulomb, like this. Okay. So finally, we have E equals rho S times R squared over 4 pi epsilon naught R when R is smaller than capital R, as we derive it in part C or part B, maybe part B. And then for rho S times R cubed over 4 epsilon naught R squared, for R is larger or equal to R. So if you like to draw it out, it will be something like this and that. So this part E is proportional to R squared. And for this part, E is proportional, inverse proportional to R squared. And this point is, this is E, this is R, this is capital R. And this is 5.6 times 10 to minus 2 Newton per Coulomb. Like this. Yeah. So we finish off this chapter in a hurry. So